So welcome to HatCheck and the HPE Developer Workshop, creating a zero trust model for microservice architectures with SPIRE and Envoy. Envoy is among the most common proxies in the cloud native computing world. And basically what we would like to do here is using SPIRE, the open source implementation of the SPIFFE standard, to integrate with the Envoy secret discovery service to create a zero trust security model within the microservice architectures, having two microservices securely and mutually authenticated, communicating with each other. So SPIRE is a production-ready implementation of SPIFFE. It's open source and it can be basically downloaded and used by everyone, but it's also an integrated part of the hybrid container platforms of HPE and GreenLake services. What it basically does is that it issues short-lived cryptographic identity documents, so-called SVIDs, which is the abbreviation for SPIFFE verifiable identity documents, to the microservices, which they in turn can use to mutually authenticate each other. The way this is basically done is integrating workloads using the SPIRE workload API of the SPIRE agent. The SPIRE workload API is an API which can be easily integrated into the Envoy sidecar. And the Envoy sidecar in return basically calls the workload API to retrieve the corresponding SVIDs, which is the secure token, to mutually authenticate with another Envoy or another workload on the other side based on its service identity. So the protocol which is then used is called MTLS, M for mutual authentication, and TLS for transaction layer security. So it is kind of an SSL type protocol which is used here, and the Envoy proxy services in our little workshop will use X509 small certificates, which are basically X509 SVIDs. But SPIRE also supports JAW tokens, so basically integrating workloads or programmatic integration with any workload using the JAW type. The component which we use is basically the SPIRE server, which is the part where the identity lifecycle is basically managed, where all service identities are registered. The SPIRE agent, which represents the integration point for the workload, in our case, the Envoy proxy, and the Envoy proxies and example workloads, which are based on the SPIRE tutorial, which is a little banking front end and a little banking back end. So in order to use the workshop, what basically we do is we call the #1 page here in your little Jupyter laptop, which is creating all the little, I would say, prerequisites in order to run through the workshop. So basically what we do here, we create everything which is required as a tenant user on the Esmeralda runtime to create the baseline, the foundation, to create the little workloads which then communicate with each other. So basically what we do now is initializing the environment in the first place. So just hit the little play button on top here to run whatever cell is selected. So they are basically executed one after another. So this is the #1, initializing the environment. Basically what's happening here is setting the environment variables to the right student ID, which is your current student ID. You have been logged on to the lab environment. It's the gateway host with a endpoint. It's the tenant name, which is basically representing the SPIRE SDS. And it's the service account, which is used to represent, basically to run all the little workloads here. So let's execute that. And for each and every command line operation, you will get the command line output as well. Let's authenticate as the tenant user. And now we have a session. And basically on the session, based on the session, we get our kubeconfig file to connect to Kubernetes accordingly. So the kubeconfig file is fetched. We configure the kube control command, and now we can execute the kube control command to create the service account student 1401. which has been created before. So here it says it remains unchanged. If there is any new service account to be created, it will be created accordingly. But that's the output we expect, and we want that the service account, which is one-to-one related to the logged on student doing the workshop, is created. So that's basically final part of the preparation. Now, to continue with the second part of the workshop, we go into, I would say, the essentials. And the essentials really is deploying the microservice application on Kubernetes with Envoy as a proxy sidecar, handling the secure service-to-service communication. So what does that mean? The workload itself, which is basically, in our case, application services represented by a backend and a front-end application, do not communicate directly with each other. They only communicate with a local Envoy sidecar, which is a configured local host port as the input of the Envoy proxy. And the communication between the workloads, backend and frontend, is only done between the Envoy proxies. So only the Envoy proxies communicate with each other, not the workloads communicate with each other. So basically, the Envoy proxy on the other side routes the traffic coming in from a front end to the corresponding backend services, but it will never be routed directly to the backend without any Envoy sidecar being involved. So that's basically enabling you an easy way to secure your communication with sidecars between workloads which do not have any secure communication off the shelf, and an easy way to integrate with SPIRE using the secret discovery service of the Envoy proxy. Now, what we will do is now create the registration entries on the SPIRE server for the Envoy proxy instances representing the different workloads, meaning the two front-end applications and the back-end application. And we will basically explore how the proxy configuration, the Envoy proxy configuration, works, and how it basically retrieves whatever we need in order to implement the secure communication. Then we test whether it is successful, and also test that it's not successful if we change something in the configuration in a way that it should not work. Also, finally, what we would like to introduce here is that we can use the Envoy RBAC, which is role-based access control filter, which is nothing else than an access control method we can use in the Envoy sidecar to basically control what service is allowed to access the backend and what service is not allowed to access the backend. So let's initialize the environment as step one. So executing that, it's basically setting the environment variables again, which is always required in order to work as the right user on the Kubernetes environment. So now let's deploy the workloads. What we have created in order to summarize all that is a customization YAML, which is basically a YAML file summing up all corresponding config maps, which we need in order to be deployed to get the workloads on and the applications on Kubernetes. So basically, to sum that up, it's the backend Envoy, it's the backend application as well, which is includes the JSON data files. It's the balances and the profiles and the transactions, which is basically representing an easy data file for a banking backend. It's the front end Envoy, and it's the front end to Envoy, which is basically the config maps which are created. The resources which we basically use for that is all based in corresponding YAML files, which are part of the SPIFFE SPIRE Envoy tutorial, which can be found on the SPIFFE.io webpage. So let's apply that. So that should be it. So you see that all the config maps have been created. The services have been created for the applications, which are deployed as services, and the deployments of the applications also have been done. So let's inspect that everything got right. So the backend is running, the front end 2 is running, the front end is running, as you can see, and you always see that in a pod, there's basically two containers. The one container is the application itself. The other container is the Envoy proxy sidecar. And here you basically see the services with their port endpoints and their cluster IP address, which is important to be used later on to test that the applications are running and that we can access the applications. So now the next thing is, now we go into really the SPIRE part with creating the registration entries for the service identities. Registration entries in SPIRE are basically the unique service identity. There is a notation in SPIRE, which is always the same, which is basically spiffy : // Then it's the domain of the SPIRE server. And then I would say the generic way forward is using the namespace and the service account and then the application service name. But everything behind the trusted domain is really free of choice. So spiffy IDs can be generated the way you want. They can be grouped in the way you want based on the forward notation with a /. So this is here where you basically can be free. We cannot be as free because using one SPIRE server for every tenant on the Esmeralda environment, we need to basically use the namespace and the service account of our current student, which means in this case, it's 1401 as the service account and the corresponding namespace. The app service name will be front-end to our backend likewise. So basically, this is how the spiffy IDs are created. In addition to the spiffy IDs, there's always the need for a parent ID, which is the agent identity. SPIRE always creates a secure chain of trust between SPIRE server, SPIRE agent, the node attestation of the SPIRE agent, which is basically checking that the node it is running on is according to its specification, and the workload identification, which basically integrates with the corresponding agent. So this secure chain of trust is always there. So this is why we need to have a parent ID representing the agent to be configured with each and every spiffy ID. Now there is an agent running on each and every node, which is an agent process. It's usually a daemon set on Kubernetes, but the agent identity represents all agents running on each and every node, which means that if a spiffy ID, a spiffy workload runs on a specific node, it integrates basically with all the agents which belong to an environment. That being said, however, there is the option to create unique spiffy IDs for each and every agent running on a certain node, so that you can basically also identify that the spiffy ID is only allowed to be operated on a certain node based on the configuration here. Now, what are these selectors? SPIRE makes a workload attestation. Workload attestation is basically interrogating your runtime environment of the nature of the workload and comparing it to the registered identity on the SPIRE server. Now, this interrogation, in our case, it's a Kubernetes namespace, a Kubernetes service account, a pod label, which we have added to the config map, and the container name, which is Envoy in our case. And this is basically ensuring that with this check, only the Envoy proxy of the backend gets the corresponding spiffy ID token related to this selector and related to this attestation. So this means no non-repudiation or non-repudiation basically in general, so that basically no service can pretend to be another service, because the selector ensures, like a type of authentication, that the service is what it claims to be. Now let's continue with creating the registration entries. We have created a little shell script for that. And you see at the shell script output that those are the entries created. It is the backend with the agent integration, with the selector container name Envoy, with the namespace test SPIRE SDS, with the pod label backend student, my student ID I'm currently logged in with, and the corresponding service account of my student ID. The very same thing for the front end, with pretty much similar selectors, only that the pod label is a different one. And also for front end 2, which has a different spiffy ID than front end 1, and also a different selector on a pod label level. Obviously, a pod label is not the most secure selector to be used to make a workload attestation. For tutorial purposes, it's fine. But in reality, this could be, for example, an image signature. It could be a unique certificate which has been issued for a certain workload. It could be anything which could uniquely select and identify the workload in order to ensure that no other workload can claim an SBIT for this identity. So let's continue and list the registration entries, whether they have been successful. You see it's the very same output. And the good thing is here you basically see the SPIRE server API command. So the SPIRE server API command is we connect to the SPIRE server container and execute the SPIRE server API and use the entry API show command and basically make a filter on my student ID, because as previously mentioned, this is the SPIRE server for all students potentially working in parallel, executing this workshop. So there could be many more registration entries for other students, not only for myself. Well, let's continue. So upon successful creation of the registration entries, all service SBITs are generated and signed by the SPIRE server. And this is what is important to mention. SPIRE works cache-based, which means all SBITs for registered identities are basically pre-generated and basically provided to the agent, and the agent, which is registered as the parent ID, has it already available. So if a workload requests an SBIT, the agent does not have to go back to the server to request the SBIT. So the SBIT is available even prior to the workload requesting the SBIT. This basically ensures a certain level of resilience. So the SPIRE server does not always have to be available to the workload, or to, well, not to the workload anyway, but it doesn't always have to be available to the SPIRE agent in order to issue an SBIT. Because the SBIT is asynchronously delivered to the agent, and it is available to the agent even before the workload is requesting it, which means that only agent and workload communication is relevant for really getting the SBIT upon need when the workload is communicating securely to another workload. So this is a very important thing to mention. So the Envoy sidecar proxy configuration. Now let's have a look into that in order to really understand how that works. So let's look at the SPIRE communication and the TLS context. So the SPIRE communication, which is the integration of the agent socket, which is the a gRPC service endpoint of the workload API, to the SDS of the Envoy proxy. So basically, what we have is always this part in the cluster section of the Envoy configuration, which is the SPIRE agent, a connect timeout, no HTTP2 protocol options, not required, and a pipe path, which is basically pointing on the run SPIRE sockets agent SOC, which is the standard configuration of the SPIRE agent. So on deployment of the SPIRE agent, this is basically the socket file, which is created as the gRPC workload API endpoint. And it really depends on your SPIRE agent deployment. If your SPIRE agent deployment is different, it's easy to find out. You just basically check the SPIRE agent config map to see what the file name is, and basically what you need to integrate here. Another way of doing that is basically simply connecting and seeing whether the file is available. That will be another way of doing that. So it's a Unix domain socket for the inter-process communication between the SPIRE agent and the workload. So let's continue. The TLS context section is basically where you configure how the proxy retrieves its SPIFFE ID and its corresponding token, which is the SBIT. So basically, what do we do here? It's the TLS certificate SDS secret config section, which is required in the TLS context configuration of the Envoy proxy. And the relevant important points are really the name which is the unique SPIFFE ID of the workload the Envoy proxy represents. So in our case, it's the backend, the front end, or the front end too. And here is the student 75 replacement. In my case, it would be, and this is what we have generated at the very beginning with setting up the environment with the student ID as the environment variable, that basically the config maps are generated with setting the student ID in as the right service account, which represents the corresponding SPIFFE ID in the complete string of my front end and my backend in my HackShack workshop. So basically, this is where the SPIFFE ID comes from. Then it's the SDS configuration. The API config source is a gRPC endpoint, and the gRPC service is basically the cluster name SPIRE agent. Let's scroll up. Cluster name SPIRE agent pointing to the run SPIRE sockets agent sock. So this is basically where it again comes together. To continue, the next thing is basically a combined validation context. What does validation mean? So if I get a token from another service, so I'm an Envoy proxy and I get a token from another service, before I can actually identify the service trustworthily, I need to validate the trustworthiness of this token. So how do I basically do that? I need to check that the SVIT has been issued by a trustworthy source. And that basically means that I check it against my secret config, which is yet again the SPIRE agent, and the domain, which is the example org domain. So this is the validation context. Then the second thing I do is basically validating incoming clients. That's optional. So I can basically already apply a filter here that I match my subject alternative name to a certain SPIFFE ID. So I can say here that it's either front end or front end 2, which I trust. I don't trust any other SPIFFE IDs, but as said, this is optional. And I could also use other filters. So this is an exact filter. I could, for example, also use a starts with or similar filters in order to allow or disallow certain SPIFFE IDs to basically start a secure communication with me as the other Envoy proxy. So inbound and outbound traffic. This is a very important thing to mention because in Envoy proxies, inbound traffic is covered by the listener section and outbound traffic is covered by the cluster section. So in our case, with the front-end application and the back-end application, the user's client, which is the browser, accesses the front-end application in clear text. The front-end application then accesses, requests its proxy sidecar, and the proxy sidecar then initiates the secure communication to the backend. So front-end to backend communication is secured. So for the front-end proxy, it's outbound traffic which needs to be secured. For the backend proxy, it's inbound traffic which needs to be secured. So basically, we have to make our configurations accordingly in different sections of the proxy configuration. So what has been described here in the TLS context part is basically added for the inbound traffic at the backend side into the listener section. And for the outbound traffic part of the front-end proxy sidecar, it's added to the cluster section accordingly to the corresponding route in the cluster section. So we always talk about routes in the proxy. So how basically does the mutual TLS communication work between front-end and back-end application? And that is really to make clear again, outbound and inbound and who's basically talking to each other. So let's look into what the front end looks like. So this is the front end configuration. So we have an endpoint for balance data and profile data path. So basically what this is used for is really querying the data. So now the front end proxy configuration. Let's get into here, describe the front end. So basically what we have here is a listener, which is an outbound proxy of the front end. which is listening to a certain port, which we had here before. No, that's the configuration of the banking app. It's all HTTP connection. And you see that there is basically no security whatsoever. As said before, what we do here is really having a front end, which is just expecting some clear text input from a browser and routes it securely to the cluster backend. So this is where the route actually is located to. And this route is actually, it's called backend, but it's not the backend service. It's not the backend workload or the backend container. It's the backend Envoy proxy sidecar. Now let's look at the backend cluster section to continue the route configuration. So here's the backend. It basically points to the backend Envoy student 1401 and the port value 9001, which is basically the listener port of the backend Envoy proxy. And it adds the TLS context as described before. And it adds the TLS context that I am the front end. This is my secret discovery service SDS integration, which points to the SPIRE agent where I get my secret from, which I also use for TLS encryption. And this is basically how I validate the other servers I'm requesting, I'm talking to. And this is basically, I make a match of the SAN exactly to the backend SPIFFE ID. And I validate the backend SPIFFE, the backend SVIT, again, using the secret discovery service integration against the SPIFFE example org domain and the SPIRE agent. So basically what's happening here is really that the X509 SVITs are mutually sent to each other, and the front end on its side delivers one with this TLS context to get one. And it also validates the one coming from the other side and expecting one coming from the other side against its SPIRE agent, which basically compares it or validates it against its trust bundle. So here, pointing again to the important parts of the configuration, the listener address listens to the port 3001, which is exposed by the Kubernetes service later on to access with the browser. And it basically configures the cluster section of the backend, which includes the socket address of the backend proxy. So it's the address of the backend Envoy student, in my case, 1401, and the corresponding port. So yeah, here pointing to the cluster context again. So this is outbound traffic of the front end, outbound traffic configuration of the front end. Now let's look at the back end, the inbound traffic configuration. So the config map here again is really output with a kube control describe config map backend Envoy and my student ID. And here the important part is that the filter is basically coming up with, let me just check, it's the backend, yeah. And that the filter is basically coming up with the TLS context, because here it's the inbound traffic which needs to be secure. And this is why the TLS context needs to be added to the listener section. It's similar to the cluster section before. So it's a common TLS context, which basically describes the TLS certificate and the secret discovery service where it comes from, the SPIFFE ID here of the backend, because it's the backend proxy side, and the pointing the SDS to the SPIRE agent, where the SVIT comes from. The validation is basically saying it's either front end or front end 2, which is allowed, and it validates it again against the SPIRE agent for the trust domain example org. Oh, this is pretty much it, similar to the cluster section of the front end. Now here in the listener section to the back end, just representing the corresponding SPIFFE IDs on the other side, basically. So here it's the backend SPIFFE ID and the front end SPIFFE IDs to which it's talking to. Now you see in the cluster section, it's only the SPIRE agent and the local backend service, and to the local backend service, it's clear text. So this is basically that within the pod, we do clear text communication, and outside of the pod, we do TLS secured and mutually authenticated communication between the Envoy proxies. Now, this is highlighting again the important sections of the configuration. So here, listening, and with this port, which has been configured on the cluster side of the front end. Here, it's the listening side of the Envoy proxy of the back end. And here, it's basically the cluster communicating to the local service. So inbound is the 9001 port, outbound, which is secured with the TLS context. Outbound is the 80 port, which is unsecured, which is clear text in our case. So highlighting yet again, listener section TLS context for the backend, because we talk about inbound traffic here. So let's test the workload authentication and the mutual TLS communication. So basically what we do is really exposing the front ends so that we have an application URL which we can basically access. Now let me access it. Another tab should be opened. And you have to click on advanced and continue because it's unsecured traffic. It's not SSL, which is by default by most of the browsers being blocked. So you have to basically manually disallow it, manually allow it in this case. Apologies for. So, and that is the other front end, which is yet again to the advanced and continue. So basically both front ends work. The one front end basically representing Alex Fergus transactions and balance, and the other one Jacob Marley's balance and transactions. So just to check on the port number, what is what? So front end is port number 10,051. And front end 2 is port number 10,053. So this is basically front end 2, and this is front end 1. So this means it works fine. So the secure communication has been configured correctly, and both Envoy sidecars can communicate with each other. Well, let's continue and try to break it, because breaking it basically means not breaking it from a, I would say, a crypt analyst point of view, but more from a misconfiguration point of view, so that the one front end cannot continue to communicate with the back end while the other front end still can. So how can we do that? How can we basically misconfigure to make one front end not work? So let's look at the backend config map update, which we are going to deploy here in order to not make it work. So here you see in the TLS context of the inbound. So yet again, to make it complete, it's the listener, it's the HTTP filter, and it's the TLS context, which is configured for it. So it's still the backend ID. This is all still correct. Now, what do we change? We remove front end 2 from the validation context of the incoming clients. So basically, this is what we do. This is what we now apply. So config map has been applied. Let's scaling the deployment up and down is basically restarting the pod. So restarting the pod means that the new config map is applied. So let's see whether it's running. It's running again since 9 seconds. Here you see the backend has been restarted 9 seconds ago. So now let's get the endpoint here again. I could click on here again, but I could also go here and make a refresh. I have to click this again. And you see the refresh is not displaying any content because the secure communication to the profile and service endpoint of the backend, the transaction endpoint of the backend, and the balance endpoint of the backend is just not allowed anymore. So backend services are not allowed anymore because the front end 2 SPIFFE ID has been removed from the validation rules, basically. Let me check whether number 1 is still working, just to show that. C number 1 is still working. So yeah, that was this point to basically get out the URL for the front-end 1 application. And I've already shown you that this is still working. Now, summing up, we have an Envoy proxy sidecar for both front ends, and we have an Envoy proxy sidecar for the backends. We have configured the secure communication based on X509 SWIPs between them using MTLS, which is mutual authentication, and TLS encryption of the traffic. And it worked for both front ends. Then we basically changed the configuration to remove front end 2 from the validation rules of the backend Envoy proxy. And then the front end 2 Envoy proxy is not allowed to talk to the backend Envoy proxy anymore, and no data is transferred. So basically what we have shown here is that mutual authentication can fail if the validation on the one or the other side does not work. And with removing the SPIFFE ID of front end 2 from the validation in the backend Envoy proxy has resulted in that. Other reasons why a mutual authentication could fail is, for example, that simply an SWIT is not provided whatsoever on the other side. So then it would simply fail even before validating the SWIT because the SWIT would not be there. Then a fake SWIT would also basically result in not being able to validate either because the SPIFFE ID cannot be matched or the validation to the trust bundle at the agent does not work. And that is a very important part. So basically, whatever we are talking about here is validating it against the trust bundle, which is we are within a trust domain. What we could do in order to extend it to multiple trust domains is SPIRE supports federation. So if you want to know more or learn more about SPIRE federation, please feel free to visit the SPIFFE.io webpage where federation features are described. But this is basically also based on looking at who was the issuer of the SWIT and whether the issue is trusted and among the federated parties which are available to an agent. So it's always done to the agent API, the workload API of the agent, which basically also provides all trust bundles to validate communication partners on the other side. Let's extend the scenario a little to not only do mutual authentication, but also to do basically access control. So what we do here is we use the feature of role-based access control within Envoy. You could also use additional access control components like an open policy agent or other access control components. But in this case, we rely on what Envoy is already giving us. What we do is updating the Envoy RBAC filter with a policy that basically allows or disallows the front-end service to obtain data from a certain profile endpoint. So in our case, the profile endpoint is allowed, and the deny deny for all other endpoints. So profile data is provided, transaction data and balance data is not provided. So this way, you could basically also control on a I would say more granular level of what is allowed to be accessed at a service endpoint, because authentication basically only negotiates the trust and the availability of the endpoints to each other, whether they communicate with each other, but then doing access control on specific services provided by these endpoints. This is where you could use, for example, the Envoy RBAC filter. So let's do that now. Basically, what we do is creating an updated Envoy config map yet again. So let's have a look at it. So you see that the listeners section basically looks the same up to the point where we go to the HTTP filter. And the HTTP filter now adds the RBAC filter to it, and it says allow to any get a method accessing the profile's URL path. And this means that it denies everything else. So it's really that explicitly the allow action configured. So profiles is allowed transactions, imbalance is disallowed. And here you say to whom, so who is allowed, and it's the authenticated principal front end. And then everything stays the same. So we have the back end as the SPIFFE ID still configured, and the front end as the corresponding allowed communication partner and the validation context to validate the communication partner. So let's deploy it. Configured. Now we scale up and down to restart the pod again. So let's look whether it runs. Not quite yet, so let's give it a couple of more seconds. Basically, what we could do is going back here and rerun it. Now it runs. So you see the 2 of 2, so both containers of the part, a part of the backend have been restarted. So let's basically go to application 1. So I could do a reload here. I have to do this again. And you see that the profile is allowed, which is Jacob Marley and its address, but no balance and no transactions. So this is basically how you can use the RBAC. So that was pretty much it. Now it's just time to do some cleanup. I'd like to ask everyone doing this workshop to really do all the cleanup steps, because it cleans up our environment to be reused for other students. So it's a very important thing to do. So please make sure that you run the code below and click the play button accordingly. So basically what we do here is deleting everything under the student's service account. So basically everything which we have created as config map, service, and deployment is now deleted from Kubernetes. But there are still our service identities being registered with SPIRE. We don't need them any longer. So let's basically delete the registration entries. So let's check. The column 1 basically says that the filter on our student ID has shows no registration entries are left in the SPIRE server for our student ID, which is fine. So the cleanup works successful. So to summarize, SPIRE basically gives you the ability to integrate Envoy sidecars as a proxy for workloads, and the corresponding secret discovery service of the Envoy proxy to enable workloads to communicate securely. And they do that based on the X509 SWITs being issued by SPIRE. What are SWITs? In order to explain what the difference is, for example, to a PKI, which can also issue X509 certificates, or what the difference is to SSL certificates. So first of all, SSL certificates doesn't suit very well to identify services because their purpose is SSL, so which is only encryption based. That's certainly one difference. Regarding a PKI, the certificate lifecycle needs to be managed by within the PKI always, which means certificates have a lifetime and have to be reissued when they reach their end of life. Otherwise, they will be invalid in the validation against the trust source, which is basically the certificate authority. And in SPIRE, you don't have a certificate lifecycle. It's automated because the SWITs are very short-lived. The purpose of SPIRE is really providing the SWIT whenever necessary to the workload, not as a general property, but only as a token after successful attestation. So if a workload, in our case, the Envoy proxies, via their secret discovery service, request the SWIT from the SPIRE agent basically performs the workload attestation. And after successful workload attestation, it basically gives out the token to the corresponding workload identity, which has been attested. And when there is a next request to by the SDS to basically request a certificate, it will basically either get the same SVIT or a new SVIT because the keys have been rolled over and the SVIT has been reissued. So it's very important to understand that SVITs are short-lived key pairs and short-lived tokens compared to PKI, and the whole life cycle is automated, and the structure on how to use it is just different, going away from property of a workload to a token to represent the workload, which is quite different. That summary is also, again, covered by the conclusion. So feel free to read through the conclusion, which also basically gives you a link to all the corresponding collateral of this workshop. This includes the workshop we have just basically, which we have on our HackShack page to give you an introduction into SPIRE in general, which is giving you a better understanding on SPIRE Server, SPIRE Agent, and how to use the APIs. It is a linking technical white paper on building a foundation for zero trust with SPIFFE and SPIRE. It's the SPIFFE concepts page, the SPIRE concepts page, public web pages of the open source standard SPIFFE and the open source implementation SPIRE. And it's the quick start, a tutorial for SPIRE on Kubernetes, which is, I would say, the basics for the workshop we've just done. And it's the tutorial using Envoy with SPIRE, which is basically explaining what we have done in this workshop in a bit more detail and leading you through what we have done today. And in addition to that, providing you the link to the GitHub with all corresponding sources you require, from config maps to Kubernetes configurations to SPIRE workload registrations and so on. So basically all the sources you need in order to play around with what we have done today and basically find out what you can do with it. So please make sure finally to fill out the survey, whether you like the workshop or not. Make sure that you log out to terminate your workshop session, and feel free to sign up in the future to the HPE developer community, if not already happened, to receive the newsletter and other collateral about the HPE developer community. So thanks a lot for your time, and that was it from my side.